1.18 to 1.25, an object is placed in front of a converging lens at a distance equal to twice the focal length as shown below. What are the properties of the image formed by this lens? So we can see that the object is exactly on the second focal length. So let's just draw how it's going to reflect. So if it's on second focal length, so it's going to go like this. Sorry, it's supposed to be straight. I'm trying my best. So it's going to go straight until the converging lens, where then it's then going to start going down. Now it should be here, like the line, but like it's really difficult to draw. And it's going to go down there. And then the second line is going to look like this. It's going to pass through the optical center, and it's going to keep on going until, well, they should be converging. I didn't draw it properly, but they should be converging at at the second focal length of here as well. Now if it's under, that means it's gonna be, sorry, it should be converging here, just please ignore my horrible drawing. So that means it's going to look something like this. That means it's going to be real, and it's going to be inverted, and it's going to be the same size. So same size, it's going to be inverted, and it's going to be, they don't have the option for real, but it is going to be real. Again, most of these cases you just have to learn them and memorize them. There isn't much explaining I can do. An object of height 4 centimeters is placed 30 centimeters in front of a converging lens, whose focal length is 10 centimeters. The image formed is 15 centimeters away from the lens. Which of the following are true? Okay, so for this one, it's just easiest to draw it out. So I'm gonna draw it here. F and then F here. I'm gonna draw the convex lens here with the optical center, the focal length, and the second focal length. So for this, we can see that they said that the focal length is centimeters. So from here to here, it's 10. But the object, which is 4 centimeters tall, is placed 30 centimeters in front of the convex lens, meaning it's going to, let's say, be around here. Because if this is 10, of course, it's going to be significantly larger. Significantly farther away. So if the object is there and it's 4 centimeters tall, let's say about that much, it's gonna, now we know how to draw it. Now we know where the object is placed, so it's going to be way easier to draw and understand. So let me just draw a better diagram. Okay, so the second focal length, the optical center, the 2F. So if it's here, the object, and it's inverted, so it's gonna go straight through like that, and then the second one is gonna go like that. Hold on, my diagram is horrible. Let me draw a better one. So this is the object. So basically, if it's behind the second focal length, it's gonna look something like this. So it's gonna go straight until the convex lens, but then it's going to refract, passing through the first focal point and down here. And the second ray is gonna go like that, straight through. And they are going to intersect over here. And the object is gonna be facing downward, like that. So that means it's inverted. And it is going to be smaller than the actual thing. And it is... Okay, so do you guys remember the formula? The magnification equals image distance. So I'm going to write ID for short over object distance. So what we have is locate. So we need to apply this formula. So the height of an object is 30 centimeters in front of a converging lens, sorry, and the image formed is 15 centimeters. So just do 30 over 15. So doing 30 over 15, you get 2, which is why the height of the image is 2 centimeters. The refractive index of air is 1 and that of diamond is 2.4. The critical angle for the diamond air boundary given to the nearest integer is blank degrees. So the formula for critical angle is that equals sine inverse, equals n2 over n1. Now remember, n2 is always the smaller index. Now if you put n2 as the larger index, like as the bigger refractive, like if you put 2.4 over 1, it's gonna show air. So that's how you know the smaller one has to be always on top. Sorry. So put 1 over 2.4 after doing like sine inverse by shift sine, you get 24.6. The light ray in the diagram below hits the glass air boundary at a greater angle than the critical angle. Show the diagram that correctly describes the subsequent behavior of the light ray. So when refraction happens, and it happens at a greater angle than the critical angle, something called total internal reflection happens. So basically, even though it's supposed to be refracting, it ends up reflecting. So this is the correct answer for that reason. Which color bends the most? Okay, so in this prism, as we can see, as the colors move like downward, so from red to violet, violet is more towards the center of the glass prism, meaning it is going to refract the most, so bend the most. And because if it's refracting the most, that also means it's going to travel the slowest through glass, which is obvious. That's why the answer is also violet. As we can see, red is at the highest point, like it's out of all the colors, it's the highest on the glass prism, meaning it's refracting less, which is why it's red. How will the beam of light continue after the lens? So for this one, it's a fundamental property of the converging lens, so there's not really much of an explanation for it. It passes through the focus. So the point on the principal axis, which the rays parallel to the principal axis refract passing through it or appear to come out of it. Okay, so you've seen in every single one of these diagrams I've drawn so far, each time I draw it, again so far, my line has passed through the focal length, this focal point. This focal point is called the principal focus. So that's basically where the principal focus is. Now also on this diagram, which is really annoying, the length from the optical center, which is here, and the focal, like the principal focus here, is called the focal length. So yeah, the principal focus f of a converging lens is shown below. The distance between the lens and f is the focal length, and the distance between the lens and 2f is twice the focal length. Where should you place the object to produce a real image? So any object at a distance beyond f is going to be real. Again, you really have to memorize the cases because there isn't much explaining to do here. Where should we place the object to produce a virtual image? So between f and the optical center. So for this, at a distance beyond f, it's basically from here to here and like anywhere beyond that. But for between f and the optical center, it's here and here. So yeah. The image formed by a converging lens is shown below. Which of the following statements describing the diagram are true? Okay, which of the following statements describing the ray diagram are true? So we can see in this diagram that the image is inverted and appears to be larger than the object, which means like a real image is going to be formed. Because a real image is going to be formed, it can only be seen by Q. We can also see that the image is larger than the object, meaning it can be a magnifying glass. And we can notice about the image that it is virtual because it is behind the object, and it is straight, like it's upright. So that's why it's not. A penny dropped into a pool, the refraction index of water is 1.33, appears to be 1.60 meters deep. The real depth of the pool to two decimal places is blank meters. So the formula for this is index of refraction equals real depth, which I'm going to write RD for short, over apparent depth, which I'm going to write AD for short. So our apparent depth is 1.6, where we're going to call RDX equals N, which is 1.33. So basically you just have to do 1.33 times 1.6, and you, after rounding, you should get 2.13, which is what I got. So a ray of yellow light is incident at the prism shown below at point O. The ray bends inside the prism, then leaves it and hits the screen at point Y. If a ray of red light is incident at the same angle and at the same point O as a yellow ray, then the red spot on the screen will be blank Y. Okay, so red light has a longer wavelength than yellow light. So that means the refractive index of the material is lower for longer wavelengths. Therefore, the red light will bend less than the yellow light when entering and exiting the prism. So, as a result, the red spot on the screen would be above Y. The dependence of speed of light in matter on the color of light is a phenomenon called dispersion. You just have to learn this one, what dispersion means. Based on its shape, the lens is a blank. Okay, so based off its shape, the lens is okay. So a converging lens looks like an oval, and a diverging lens is like an hourglass. That's how I think of it. So yeah, these are the two shapes that you need to know. So it's a diverging lens. An incident ray of light in a glass hits the boundary with air. What happens to the ray when its angle of incidence is less than the critical angle at the glass-air interface? Okay, so what is the critical angle? The critical angle is the angle of incidence at which light travels, like from a more dense to a less dense medium. Specifically, my bad. At a refracted angle of 90 degrees, which causing it to travel along the boundary. So if the angle of incidence is less than the critical angle, that means it just refracts normally. But when it is greater than the critical angle, it undergoes total internal reflection. If you guys remember in the last physics periodic, this came as written part. So the figure below shows a ray of light from the air into a block of ice at point A. The critical angle at the ice air interface is around 50. So basically it's less than 90 degrees, like less than the critical angle basically, which means it's going to just refract normally. The refractive index of the ice block to one decimal place is... Okay, so for part D, what you have to do is, we know that the refractive index of air is 1 times, and then you're going to do sine 50, because we're using Snell's law here, equals x, which we don't know, times sine 30. My bad. So there's a mistake in this question because you end up doing sine 50 over sine 30. You should get 1.5, but they give the answer here as 1.3, but that's a mistake. A beam of light strikes the surface in the interface between water 1.33 and air at an angle of incidence 40, shown in the figure below. Select a diagram that shows the propagation of the incident ray. It's going to be tilting away from the normal because it is going from more dense to less dense. So the only one tilting away from the normal is this one. The angle of reflection is, now we know that the angle of incidence is 40, meaning that the angle of reflection is also going to be 40. The angle of refraction to the nearest whole. So for part II, we're going to use Snell's law. So 1.33 times sine 40 equals 1 times sine, and we don't know, so we're going to call it x. So after putting this in your calculators, you get the answer for this, and then you take this to the other side, just the sine. So you get sine inverse, and whatever you got, 1.33 times sine 40. Do not write it like this on your calculator. Okay, so you should get 59. At what angles would the beam of light not propagate through air? Okay, so we can see that here it's moving from a more dense to a less dense medium, and it is not going through total internal reflection, which is why the answer is greater than or equal to theta. Okay. The figure below shows three rays of light approaching two separate optical devices. So the first one is a diverging lens, and the second one is a converging lens. So diverging means it's going to split, and converging means it's going to meet at one point. So if diverging means it all comes out, like it starts at one point and it splits, it means the first one's correct because it starts from this point and it splits into many. And this one, the second one, is wrong because it doesn't start from one point. And converging means it meets at one point, so therefore this is correct. So these two are correct. An object is placed 15 centimeters from a lens with a focal length of 10 centimeters. The lens produces an inverted image of 30 centimeters from it. The magnification of the image is... Okay, so the formula, which I said before, is magnification equals image distance over object distance. So the object distance is 15 and the image distance is 30. So 30 over 15, which is 2. A ray of light traveling through the air strikes a glass prism perpendicularly as shown in the figure below. The speed of light in glass is 2 times 10 to the power of 8. So we know that the speed of light in vacuum is always 3 times 10 to the power of 8. And if they gave us a speed of light in glass, which is 2 times 10 to the power of 8, to find the refractive index, we just have to do 3 times 10 to the power of 8 over 2 times 10 to the power of 8, and you get 1.5. The critical angle at the glass air boundary to the nearest whole number is... So we're going to use the critical angle formula. So you do sine inverse equals 1, which is always, you have to memorize the refractive index of air, which is just 1, and the refractive index of glass, which we got here, which was 1.5. So you do that over 1.5, sorry. So 1 over 1.5, so they get 42 after rounding. Select the diagram which directly shows the propagation of the ray of light. So first it's going to travel normally until, of course, you actually hit the glass itself, where it then bends, like refracts, and then it will refract again. So this one. The diagram below shows the ray of light incident from O and striking a converging lens. We assume that the distance OP is the focal length of OP equals P. Okay, for this one, it's another one of the cases we can see it's at the second focal point. So it means after this, it's literally just going to travel straight, meaning it's going to cross through A. Okay, so we can see in this case, it's a little bit like, it's in between 2F and F. So when it's in between 2F and F, the first ray is always going to look like this. It's always going to go straight and then upward. And the second ray is always just going to go straight through the optical center. It's never going to look like the middle one, like ray Y. So that means ray X and ray Z are correct. Again, please learn the cases, it's super important. Red light travels faster than violet light in glass, thus violet light has a refractive index larger than that of red light. So because violet light is highly refractive, it means it's gonna go normally inside the prism, and then after the prism, it's going to graze the surface. Okay, this one you just have to learn it and memorize it, whatever. So for the diverging lens, it's virtual and it's upright and it's smaller. And for the converging lens, it's between f and 2f. It's positive. It's, I think, inverted. Hold on. Yes, and it's larger.